scale them with rho c minus rho to the nu, and they all follow one another. It all collapses, right? And this critical exponent here is the critical exponent, okay, that's known for that. You could have fit the critical exponent, got the critical exponent from this. You can do 2D icing as a function of temperature. Here's what you get by the scaling procedure, if you like, the real space procedure, and here's how it collapses, right, all to the same curve, which says essentially everything here is just a function of delta over the correlation length, the compression thing. Here's another model. This is one of Dove's favorite models because his name is on it, okay? And it's a jamming model, a traffic jamming model, okay? Well, the rule is red guys can only go to the right from where you're looking, and blue particles can only go down, and they can block one another. So that guy can't move while that guy is there, right? And it's actually a fairly beautiful model. It shows you self-organization in a really weird way. This is the dynamics of it, right? And this is in the jam state, and so this thing is going to go to completely jammed, okay? Like, come on, like that, okay? Now you look at this, okay? And it's known that this is a transition from where everything is flowing to where they're jammed. That was known before. It's also known that's first order. Here's what you get from the CID, okay? And what you can see is a jump here. You can actually see that there's coexistence in some regions, okay? And here's what wasn't known before. There's another transition. People had hinted there might be another transition before. But in the jam state, you can have a single cycle here or a different winding number, and there's actually a cascade of first order transitions over here that was never seen before that you find from this. I mentioned Rudin-Shapiro before. Rudin-Shapiro is the sequence which is actually given just by essentially an inflation rule by a matrix. A goes to AB, B goes to AC, etc. If you substitute in A, you can just write out what this is. An algorithm that gives you this entire sequence is a very short algorithm, okay? So its entropy is 0, and I showed you its entropy goes down with the size of the system. But I also told you this guy has the property that its two-point correlation function is flat, okay? If you do S of Q or G of R, it's just flat at 1, okay? So it looks to something like that, like a random sequence, but it's not random at all, okay? The interesting thing is, if you multiply by anything with this, so if you multiply any sequence by a random sequence, you get a random sequence, right? The interesting thing is, if you multiply anything by Rudin-Shapiro, you don't get something random, but you get something whose spectral functions, S of Q or G of R, is just flat. So here's showing it to you. Here it turns out is S of Q, the structure factor, density correlation function for a transform, essentially, for an Ising model, which has strong correlations in it depending on the temperature. This is the temperature over here. So the lower you go, the stronger the correlations are. You take this and you multiply it by something that's random, and S of Q, that's this red line over here, it gives you something that's flat like that, okay? Like that. Okay? You multiply it by Rudin-Shapiro, and you get something which is the orange line, which is even flatter. Okay? But now you compress it after you multiply by random. If you compress it after you multiply by random, it's flat and random. This is a function of temperature, which is off the screen over here. I mean, Ising 2D, this is 1D Ising actually. So 1D Ising by itself looks like that. Is that right? Yeah, okay. Looks like that. And you multiply by Rudin-Shapiro, and you see the information is still there. It's changed, but it's still there. You can cloak with this. You multiply by Rudin-Shapiro, and for two-point correlations, there's nothing there. If you want to get your information back, okay, you multiply by Rudin-Shapiro again, and it's gone, right? Okay? And there are lots of different forms of Rudin-Shapiro, I should say. Okay? You can take 1D Ising over here. You can do the decimation that I told you before to get the correlation length, the scaling, and it collapses to this. You take the Rudin-Shapiro Ising, and you collapse it collapses that, which isn't quite so good because it turns out this goes away. This collapses better and better the bigger the system you have. 1D Ising has a correlation length which is exponential. I'm done. Did I use up the time? Or do I have time left? 3 minutes. Oh my God. Okay. So the main thing you should take away from this is, without knowing anything about the order of a system, what the order is, you can find out whether it's ordering. You can find out information about critical exponents. What else do I have? I've shown you equilibrium, non-equilibrium, on-lattice, off-lattice systems. What can we do next with it? We're going to do more with experiments. We want to look at stuff that the people in the glass community who were here 2 weeks ago giving a really nice symposium had to see whether you can find order in the glasses. We want to look at the universe, okay, because there's data on position of stars as a function of time to see whether there's any evolution in that, okay? There should be, I've shown you just classical examples of this. You ought to be able to do this for quantum systems as well, but I don't know how to yet. You can look at things like memory. You can also look at the stock market. And we haven't even started looking at what you can do with time, since you can compress with time as well. And that will give you things like glassy systems and other things like that. And I'll conclude with something with Stefano, to make things clear, with what Stefano found, I think, yesterday in some newspaper that he was reading, which is the Kolmogorov directions, okay? That is, if you want to get home tonight, okay, instead of saying, okay, drive this way for this much, drive this way from this much, drive this way from this much, what you should do is take every left turn that doesn't put you in a prime numbered highway or street named for a president, and you'll get home. And that's the Kolmogorov way of doing it. Okay, thanks.
It's a pleasure to be here and an honor to be able to tell you about the search for dark matter with the Xenon project. The goal of this project is to find dark matter particles as they scatter in this material which I love, which is xenon, liquefied xenon. And we try to do this by building and developing instruments, detectors, which are ever more massive and at the same time ever more quiet in the sense of noise, because the signal, as I will show you, is extremely rare, of course. And so we have been inventing ourselves in making these detectors better and better for the past 15 years. And as we improve the technology and the experiments, we continue to be hopeful to find a signal. So far, as David said, we have just excluded orders of magnitude in terms of the interaction with which these dark matter particles care to do something with the standard matter which we made. But as we move forward, I have not lost hope, so we keep searching as we build the next yet experiment, which I will show you towards the end. And at the end, I never felt more excited that finding nothing today is actually as important as to find a signal, because we either will, hopefully in the next 5-10 years, we'll find this signal finally, even a glimpse of it, or we will exclude, or we will find what dark matter is not. And that's equally essential, because we will drive theory to search somewhere else, to find answers in other direction. And so that's the goal of the project. The question of the nature of the dark matter which prevails in this universe remains a mystery. It's the question we're trying to answer, at least with our experiment. And it's a fundamental question which connects physics, fundamental physics, cosmology, astrophysics. And how can we resist not to find an answer to this question when we know that the universe is actually dominated by this form of matter? The matter which we are made of, the standard matter, the atoms that we know, is only a tiny fraction, only 5% of the matter energy density of the universe is in normal matter. So, in fact, this dark matter which prevails is the glue which keeps the universe together, because from our own galaxy, you saw that picture in the first slide, from our Milky Way to every other galaxy, from clusters to the larger scale structures that we observe, the gravitational attraction due to dark matter is what keeps everything together. It's the glue which keeps the universe together. And perhaps the most direct way that we have to see dark matter, the presence of dark matter, is through this phenomenon of gravitational lensing, the distortion of light due to the presence of mass. And in fact, last year, the Dark Energy Survey, studying the distortion due to weak lensing of 26 million galaxies, has come up with the first and very detailed map of dark matter distribution. And what is amazing, and so this is the left plot here, the region with the reddish color are regions, structures where dark matter is more prevalent, and the blue has less dark matter. But what is relevant in its first map, which is just a piece of the sky, is that the growth of these structures from their moment of formation to today can actually be nicely explained by cosmological models which are the basic cosmology, which is based on the fundamental theory of particle physics, on the standard model, on precision cosmology, through which we know precision cosmology in the last 20 years has given us an amazing amount of information about the origin, the evolution, the expansion of this universe. And we know from this precision cosmology that these two dark components of the universe, the dark matter on one hand and the dark energy on the other hand, we know these two dark components with high precision. Unfortunately, what we don't know is really their true nature still. So we remain unclear about the nature of these dark components. And while the next generation cosmological survey, with their increased capabilities to trace the evolution of the universe, will hopefully give us an answer on the dark energy question, if it is a cosmological constant, is a new dynamical field, or maybe we have to change general relativity. I think the answer to the other dark question, what is dark matter, will yes come a bit from cosmology, but also directly from experiments on Earth, such as our experiment and similar experiment, or from experiments at accelerators. Together, the synergy of these studies hopefully will help us understand the nature of this dark matter in the next decade and dark energy. So before I move on, I mentioned this ordinary matter. What is worth to point out, especially among us as we look at the night sky, actually the 5% which constitutes the standard matter as we say, is really not all what we see. What we actually see in stars, in planets, everything which emit light at some wavelength, is actually only 1% of the total matter in the universe, because the rest is in gas, mostly hydrogen, helium, which fills the halo of this galaxy, every other halo, and all the spaces between these galaxies. So only 1% is actually what we can see, which is actually daunting. The 85% of the matter in the universe is invisible, or we say it's dark, and we say it's dark because it doesn't emit or absorb light at some wavelength that we can see. The big question is, finally, I told you already, was the big question, what could this dark matter be? And one of the, despite its prevalence, 85%, as I said already, we have not directly seen it. What could it be? An attractive idea, a leading hypothesis, is that dark matter is a thermal relic, something which has been left over from the early phase of the universe, when it was 1 billionth of a second old, after the Big Bang, so when it was about 100 GeV or so hot at that very high temperature. And while no particle of the standard model is a viable candidate for dark matter, the young universe was hot enough to produce these massive new particles, which which we are here hoping to detect in the laboratory on Earth. So a relic of the Big Bang, and if these relics are there and they're stable, if they're stable, they can still be around today and fill the halo of the Milky Way. And from the amount of dark matter in this Milky Way, we can infer how many of them, of this particle, can reach our detectors. But I wanted to also point out that while we talk about this class of relics, we refer to them generically as weakly interacting massive particles, or WIMPs. The class of WIMPs is just one candidate of dark matter. It has been very popular. As you can see from this plot, the height of the thing there is how many papers have been associated with this specific candidate, but it's not the only one, the WIMP class. It's very well motivated theoretically because many theories behind the Standard Model give us naturally WIMP candidates, such as the lighter supersymmetric particle, the neutralino in supersymmetry, or the Kaluza-Klein photon in extra dimension. So the WIMP has been really favored for many, many years, and is not yet dead. We're looking desperately for it. But as you can see, we have particles which span a huge range of masses. This is the dark matter candidate mass in electron volt, and you go from fuzzy dark matter, which is unbelievably tiny, to the axion, for which is also well motivated, for which a lot of nice searches are going on today, to